back to another video of Tom Engineering. So today, I got this big shipment of components in the mail, and what better way to get familiar with them all than to use them all in one build. I already had an idea in mind, because for some time now I've been wanting to make a robotic arm, and although it's not a necessity, I really wanted the base of the arm to be a harmonic drive. And since my YouTube career can't yet provide the funds to buy one, that's exactly what we'll be building in today's video. Now, before we move on, let's talk about what a harmonic drive actually is. If you already know, feel free to skip this part. Okay, so technically it's called a strain wave gear, and it relies on elastic dynamics, which is a fancy way of saying we're purposely bending parts to make it work. Because the teeth are constantly meshed at 2 points, there's virtually zero backlash, meaning no sloppy movement or wiggling. That makes them absolute lifesavers in precision robotics. If you're dealing with a robotic arm, or even dealing with aerospace components, harmonic drives are what let you position heavy loads with pinpoint accuracy. In other words, they're a great way to have a big gear reduction in a small area. Alright, with all that out of the way, let's see what we're working with. First, the muscle of the entire project, the NEMA 17 stepper motor. These are the gold standard for 3D printers in DIY robotics because they offer excellent holding torque and precise position control. Of course, a motor is useless on its own, which is where these motor drivers come in. These act as the translator between our microcontroller and the motor itself, handling the high current and telling the NEMA 17 exactly when and how far to go. Then there's this part that's easy to overlook but saves the whole build: heat set inserts. Threading steel screws straight into plastic is a recipe for stripped threads, so instead, a soldering iron melts these brass inserts permanently into our build, giving us strong, reusable metal threads. We also have screws to hold it all together, some different sized bearings, and last, but certainly not least, a roll of TPU, a flexible printing material and key to the elastic part of this design. Okay, with everything accounted for, let's jump right into the design process. Like always, I started with a ton of research. I looked at existing designs, gear theory, and way too many pages of this textbook until I had enough context to start sketching. My first design had a module, or a fancy way of saying tooth size, of 1, and a ratio of 30:1. All the math checked out in theory, but after modeling, I realized that it was way bulkier than I'd wanted. So I dropped the module to 0.8, updated my math accordingly, and started on my new model. Thankfully, SolidWorks has a great gear generation tool that saved me days of manual drafting, but I still spent the better part of a week creating and adjusting other components. As you can see here, this is what the final design looked like. It consists of 7 custom 3D printed parts along with the various purchased components I mentioned earlier in the video. My goal was to make it as compact as possible while still maintaining decent efficiency. I also had to consider the capabilities of my printer throughout the build, so I couldn't make any component, specifically the gear teeth, too small. With all that said, I was pretty proud of how my design came out, but I couldn't get excited yet because I still needed to print and assemble it. Unlike in my last video, this time I was pretty careful while slicing and choosing printing specifics, especially while printing my first TPU component. Let's see how they turn out. I was pretty happy to see that mostly everything printed well on the first try. Unsurprisingly, the only issue was with the TPU component where I got some webbing. Thankfully though, it was an easy fix, and with all the components ready, it was time to assemble them. Now, although it looks pretty awesome, we still need to see if it works. I wrote some basic code and assembled the simple circuit. If everything was done correctly, we should see it spin when I press this button. Okay, it's moving, which is a great sign, but we still need to know if it's working correctly. To do that, I put my harmonic drive through 2 tests. First, I input a code that made the motor run for 30 full revolutions. If I did everything correctly, this will amount to 1 full output rotation. For my second test, I wanted to see how repeatable it was. With no proper force gauge, I had to get creative. I attached an arm to the output of the drive, then mounted that and a suitcase scale to a platform. I connected them using an elastic at the arm's 10 cm point, ensuring it became taut when they were perpendicular. Then I had the drive move continuously through the same range of motion. I ran that test multiple times, and the scale consistently read about 45 grams when perpendicular and 280 grams when about 30 degrees past that point. While this setup isn't suitable for accurately determining the maximum torque of the drive, it does give us a way to demonstrate the repeatability of the prototype. Based on these results, I'm satisfied with how this project turned out, and I'll more than likely be using it for a future project. I was also pretty happy to see that everything worked well on the first try, considering I pre-wrote the entire script to this video assuming that would happen. However, if I were to make a second one, I would make a few small changes. I'd use fewer screws and heat set inserts to secure everything in place. This would make it easier to assemble while still keeping it secure. A proper mount would also be helpful because, as you probably noticed during my tests, I still needed to hold it in place. And lastly, a more compact and mobile circuit would be an amazing addition, because right now I can only operate the harmonic drive a set distance away from my computer. Overall, I had a lot of fun making this, especially since it helped me get familiar with a bunch of components that I'd never used before. I hope that at least one person watching this has also learned something, or is even using this video to create their own harmonic drive. As always, if you have any questions, suggestions, or feedback, please let me know in the comments below. Thank you all for watching, and I'll see you in the next one.